Welcome friends to a short video about implicit differentiation. One of the points in Calc 1 classes that we talk about is implicit differentiation, and in my experience, number of students have had problems with this concept. A lot of times it results in the notation being used. Frequently, textbooks will use Newton's notation to indicate derivatives, when in this situation you want to use Leibniz notation. The strength of Leibniz notation over Newton's notation is that it gives us the ability to manipulate the derivative algebraically. And that's the strength of doing this implicitly, as it relies very heavily on algebra. So I'm going to walk you through. Here's just one problem, one example. Of course, it gets much harder than this the farther you go. But when we take a second to look at it, you can see here and here, it's going to require us to use the product rule for derivatives, right? And then beyond that, we're just looking at using the power rule for each individual derivative once we've expanded out. So the first thing that we're going to do, friends, is we're going to derive both sides. We're going to put the derivative operator on both sides. This will maintain equality, and very much there's a zen to doing these kinds of implicit differentiation, right? You have to just trust the process, know that it's going to work out, and so let me show you that now. So we're going to use Leibniz notation. That's our d over dx notation, and we're just going to derive both sides like we know it's going to work, and we're going to put down our derivative with respect to x. Then I'm going to use parentheses to write the expression 2x cubed plus x squared times y minus x times y cubed, close those parentheses, equal to d dx of the constant function 2. All right, well, some of these are easier than others, right? So real quick, what I want to do is I want to address the right side. We know the derivative of a constant function, right? Remember, the derivative gives us clues to the slope, and the slope can give us clues to the derivative. And we know that when we take the derivative of a constant value, we get 0. So that's a real easy derivative to take right off the bat. It simplifies. Now we're just really looking at the left side. One of the things that we learned along the way, wherever your journey in calculus might have taken you, is that the derivative of a sum and a difference, like our expression here, can be rewritten as the sum and difference of the derivative. So we're going to distribute the derivative over the operation, and what we're going to get on the left side is d dx of 2x cubed plus d dx of x squared y minus d dx of xy cubed. And that's going to be equal to 0. Okay, so far so good. Now the next thing I'm going to do, maybe you're looking at this first term already here with its derivative, and you think to yourself, oh, I remember the power rule. It might have been a while since you've been in calculus, but I remember the power rule, and that's going to be 6x squared. We'll get to that. That's an easy derivative, and we'll get to the point where we sweep through and take all the easy derivatives. But before we do that, I want to look at these second two terms and their derivatives, each of which is going to require a power rule, a product rule. So then the next step, I'm going to write out that product rule. And it's going to be no change to the first term, so that's going to endure d dx of 2x cubed. Now we're going to do the product rule here. So we're going to have plus d dx of x squared, and I'm going to put that in parentheses. And then in parentheses, to indicate the multiplication, I'm going to put y. Okay, now the second half of the product rule has me sum that term with x squared times the derivative with respect to x of that variable y. Okay, and see right here, see this is another easy derivative to take. And like I said, in the next step, we'll sweep through and take all the easy derivatives. But I want to call your attention to this derivative. Here we're having the derivative with respect to x and an expression in y, and that's where the implicit step is going to come in, and we'll get to that. Now the next thing I'm going to do is I'm going to write this minus, and then I'm going to drop in a nice big hard bracket, just like that. And the reason I'm going to do that is because I'm going to apply the product rule here as well. But I want to make sure that this negative gets factored into both terms within that product rule. So it's going to set up very much the same way here. If you remember the way the product rule works, we have parenthesis d dx of x times y cubed, put that in parentheses also, plus x times d dx of y cubed, and we're going to close that big bracket off. Remember, I did that so I don't forget to distribute this negative. And I'm going to squeeze it in here. I'm running out of board space, but that's okay. I'm going to squeeze it in here. It's all equal to 0. Okay, no change to the right side of this equation. We're pretty much just doing our work on the left. Now we've expanded out. Let's go ahead and we can come back through and take a second to distribute this negative here. So when we distribute this negative, this first pair of factors is going to become negative. So I'm going to remove that. And then it's going to distribute here as well. And I'm just going to take my finger, erase that. Now it's gone. And we're going to put the minus in there. And that allows me to take that back bracket off as well. Did you see what I did there? See, I had a sum, right? But I wanted to make sure that the negative here from the step before got distributed to both of those terms in order to maintain equality appropriately. This is the distributive property. Okay, now I'm very happy with that. So let's go through and we will, in the next step, take all of the easy derivatives. What do I mean by easy derivatives? I'm talking about this d dx, right? The derivative with respect to x of an expression in x. So that's an easy derivative, that's an easy derivative, that's an easy derivative. Okay, that's what we're going to do in the next step. And then in the final step, we will take, we will begin the implicit process. It's not a final step. I take that back. All right, so in the next step, we're going to take all of the easy derivatives. So right here, the derivative with respect to x of 2x cubed using the product, using the power rule is going to give us 6x squared plus the derivative with respect to x of x squared is going to be 2x times the y. We're going to just bring this down. No change here because this is an implicit derivative that we're going to do. So this is plus x squared times that derivative operator with the expression there being y. Here's another easy one, d dx of x. Okay, that's linear, right? That's just y equals x. That's a straight line. And the derivative of that is 1. So this is now going to be minus, and I would write 1 times y cubed, but we know what anything times 1 is. It's unchanged. This is the multiplicative identity. So here we resolve this this term, and we have resolve the derivative of that term, and we're left with just y cubed. And then here I'm going to copy that straight away down because we'll do the implicit derivatives in the next step. Okay, so d dx, that's the derivative with respect to x of y cubed, and still equal to 0 on the right. Okay, very nice, very nice. Now remember, there's a reason why I chose to use Leibniz notation over Newton's notation, and it's here when we do the implicit derivatives that we really see the strength of this. So I need to make some room to work, so I'm going to erase the 4 lines, and then I'm going to rewrite this 5th line at the top, and then we'll keep working. How does that sound? In fact, I can erase this part too, right? You know we're working on implicit differentiation. Now remember, friends, this does get quite a bit harder. This is just meant to be an initial example, kind of like first gear, get the car rolling from the stop, but it's up to you to keep going with this, okay? So I'm just going to copy it verbatim up at the top so we have some more room to work. 6x squared plus, are you okay if I just write 2xy like that? Is that okay? And then we don't need those parentheses, right? And these terms are done. We're going to leave these terms alone. So now the next term is this product x and the derivative with respect to x of y, and then we have minus y cubed, okay? And then we have minus, and the first factor there is x, and the second factor is the derivative with respect to x of y cubed. And remember, it's all equal to 0. Okay, so far so good. Now we'll get rid of this. All right, now, of course, anything times 1 remains unchanged, right? This is known as the multiplicative identity. So I'm going to employ that now, and I'm going to multiply each one, I only have 2, of my implicit derivatives by 1. But I'm going to specially choose the one that I'm going to multiply it by. All right? So pay attention here. So the first 2 terms, no change there. We have 6x squared plus 2xy. Okay? Now here's where I'm going to initiate the first change. So it's going to be plus, we'll keep the parentheses around that x for right now so that it's separate from our work with the derivative. Now we're going to write the derivative with respect to x from right there to right there. Now I'm going to write my 1. It's a very special one. It's an important one. And it's in the form dy over dy. Okay? You'll see why this is clever. All right? And then we're going to bring that term in here. That's just y. Okay? Minus y cubed minus, and again, we're keeping the x in parentheses. And then here we're going to do the same thing. Here's our derivative operator with respect to x. Now we're going to write in our 1. We can do this. Anything times 1 is unchanged. So we can do this. And that's going to be equal to 0. Okay? Now, like I had mentioned at the beginning of the lecture, the strength of Leibniz notation is it allows us to manipulate the derivative algebraically. So the only thing I'm going to do here and here in the next step is I'm going to switch the numerators. I'm going to switch the numerators, and then I'll explain what that does for us. What are the mechanics of the mathematics that does for us, okay? So first 2 terms. Again, no change there. We have 6x squared plus 2x times y plus, here's our factor of x right from here, straight down, okay? Now here's where I'm going to do the work, and I told you I'm going to switch the numerators. I'm going to switch the numerators. This is okay. This is done under the property of commutativity. This is a fundamental property of algebra that I'm employing. There's only 5 of them, and the property of commutativity is one of them. So this is a legal move. I'm allowed to do this. See, I got the dy over dx, so now that's the dy right there, okay? And that dx goes right there. Now I've got this d, and I'm going to move the d over here. See, dy, like that, dy. And that's of y, just like that, all right? Minus y cubed, minus, again, that x stays in its parentheses, all right? And here again, we're gonna switch the numerators by the property of commutativity. So I write dy dx, just like I did here, okay? That dy right there, and that dx goes right there. Then that d is in the next spot, d dy. And that is y cubed. Close those parentheses. And remember, the whole thing equals 0. All right. Now, what did I do here? This was really the key step. From here to here is what allows me to move forward. Because now what I have is I have a derivative operator with respect to y. And so what I did is I took the derivative operator with respect to x, and by very carefully choosing the right one to multiply it by, I'm able to rework that derivative into an operator that has respect for the variable y. And I did the same thing here too. Now I can take those 2 derivatives. So let's do that. No change to the first term. First 2 terms, 6x squared plus 2xy, okay? Plus, and again, we're going to keep the x in the parentheses just like that. Then we've got dy dx like that. And now what is the derivative of y? Well, that's a linear y. You notice the exponent is only 1 there. And so because of that, we get, and I'm just going to put it in here so you can see it, the derivative is just 1. Okay? In the next step, we know anything times 1 is unchanged. And so I'll remove it in the next step. But let's leave it in there for right now just so you can see it. Minus y cubed, that doesn't change. Okay? minus, and again, we're going to keep the x in the parentheses just for one more term. And then here, we're going to take the derivative with respect to y. So we get the dy dx comes through. Then we take the derivative with respect to y of 3y. This is power rule. And that's going to give us 3y squared. And that's equal to 0. Okay, we're almost there, my friends. We're almost there. Okay, in order to achieve the derivative, to get a single expression for the derivative using the implicit technique, the only thing we need to do now is solve for dy dx. And that will be the derivative that we're looking for. Okay, the hard work is now over. We were able to work through all of the algebraic techniques to allow us to take this implicit derivative right here. That's what we did. Okay, d dy of y becomes the 1, and d dy, or the derivative with respect to y of y cubed, just becomes 3y squared. Okay, so what I'm going to do next is I'm going to move every term that does not have a factor dy dx in it. Okay, this is allowed under the addition property of equality. I'm going to move all those terms to the other side. So instead of 0, we're going to get something new. Okay, so here, I'm going to start here in the next line. I'm going to start right here. And what do I have? I have x times dy dx. I'm not going to write the 1. Okay, it's just x times dy dx, just like that. Okay, and then here, okay, we're going to clean this up a little bit. We're using the property of commutativity, and we're going to write minus 3, that 3 right there, and then that x right there, and then the y squared. Just puts it in a nice order for us, nice alphabetical order for our algebra. All right, and then lastly, the dy dx goes. And that's going to be equal to minus 6x squared minus 2xy plus y cubed. Those are the 3 terms. You see, this term does not have the dy dx. This term does not have dy dx. This term does not have dy dx, so they get moved to the right side. And the only terms that I have left on the left side have a factor of dy dx. In the next step, I'm going to use the distributive property. Again, this is another one of those fundamental algebraic principles in order to factor out this common factor of dy dx. Remember our end game is we're trying to solve for dy dx. So the only thing we want on the left side is that derivative with respect to x. Okay? So let's factor it out. 2 more steps. We're going to factor it out, and we're going to have dy dx. Now this one is from both of these. So that only is going to leave x minus 3xy squared. Okay? And on the right side, no change there. On this step, minus 6x squared minus 2xy plus y cubed. Okay, we're almost there, friends. We're almost there. In the last step, we're going to use the multiplication property of equality. Again, another fundamental property of algebra. And we're going to divide both sides by this expression. And then what have we done? We've achieved our goal of isolating dy dx, and we'll have the derivative derived implicitly of the initial expression. So let's look at that, okay? Here it is, dy dx. This is the derivative we're looking for. Dy dx equal to all of this stuff in the numerator. Minus 6x squared minus 2xy plus y cubed all over, what's this over here? Our denominator, x minus 3xy squared. All right, friends. Let me remind you that if this is the first time you're looking at implicit differentiation, this might seem very long, very difficult, but each step conforms to basic algebraic properties, and it is well within your ability to do. The examples, the problems, and the homework, the quiz, the exams that are forthcoming are going to get harder. And the only way to improve your skills is to practice. Go ahead and email me if you have any questions. Have a good day, friends.